Hello, I am Bruno Ordozgoiti, and this is Finding Large Balanced Subgraphs in Signed Networks. I am a postdoc at Aalto University in Finland, and this is joint work with my colleagues Antonis Matakos and Gionis. So a little bit of context. We're working with signed networks, which are just like your everyday graphs, except for the fact that each edge is labeled with either a positive or a negative sign. Down there you can see an example of a signed graph and the corresponding adjacency matrix, where we represent positive edges with a +1 and negative edges with a -1. We're concerned with the concept of balance in signed networks, which is a representation of the old adage, a friend of a friend is a friend, and so on. So on the right you can see a depiction of the 4 possible non-isomorphic signed triads. The 2 on the left are balanced, while the 2 on the right are not. And you can check by yourself that the ones that are balanced are consistent with this idea of a friend is a friend, and the ones that are not balanced are not. So the formal definition of balance is as follows. We define the sign of a cycle to be the product of its signs, and we say that a graph is balanced if it has no negative cycles. A characterization of balance that is interesting to us in this context is the following. We say that a graph is balanced if it can be partitioned into 2 sets of vertices, S1 and S2, such that within each of the sets there are only positive edges, and between the 2 sets there are only negative edges. So here you can see an example of a balanced graph, and you can clearly tell that this partition is indeed possible. So an example of where we might see balanced graphs occurring in real data is polarized communities in social media. So if we take a graph in a social network and we interpret the signs of the edges as representing whether interactions between users are friendly or hostile, then a balanced graph might represent polarized communities. And we might be interested in detecting this because this might signify the presence of an unhealthy discussion taking place in the social media platform. So we're interested in the problem of finding balanced subgraphs. In general, we should not expect signed graphs representing real data to be balanced. So it might be interesting to find balanced subgraphs in these networks and have them be as large as possible. So formally, this is the problem of the maximum balance subgraph. Given a signed graph, we are asked to find the graph induced by a subset of the vertices of G, that is a subgraph of G, which is balanced and is as large as possible. This is an NP-hard problem. So our contribution is a heuristic for this problem. We rely on spectral theory for signed graphs. So spectral theory in the case of signed graphs revolves mostly around the signed Laplacian, which is defined very similarly as the Laplacian for unsigned graphs. with the difference that the degree matrix is comprised of the unsigned degrees of the vertices. So an entry of the degree matrix will be the sum of the edges incident on the corresponding vertex regardless of their sign. And the reason we are interested in spectral theory is because there is a characterization of balance which relies on the minimum eigenvalue of the Laplacian. So a connected graph is balanced if and only if the minimum eigenvalue of the Laplacian is 0. So based on this fact, we propose a greedy algorithm to find a balancer graph, which consists in, at each step, removing the vertex which yields the most significant reduction in this minimum eigenvalue. So that is, we seek to remove the vertex that most improves balance in this sense. And this allows us to design a basic algorithm for finding a balancer graph. We just remove vertices according to this criterion until we find a balancer graph. The problem with this approach is that it is very slow. So we will propose a series of speedups. So the first thing we do is, instead of computing the reduction in the eigenvalue that will be achieved by removing each of the vertices, we derive an upper bound of this new minimum eigenvalue. A key advantage of this upper bound is that it's very fast to compute for all vertices. So essentially with a matrix vector operation, we can compute this upper bound for all of the vertices, for the resulting minimum eigenvalue from removing any of the vertices in the graph. This is a depiction of how the upper bound looks for a couple of real small signed graphs. So as you can see, it is empirically quite tight. So it should be a good way to select which vertex to remove at each step of the algorithm. So relying on this bound, we can improve our original greedy algorithm to rely on this upper bound instead of the exact value of the new minimum eigenvalue of the Laplacian. But this can still be slow, as we need to update the bound every time we remove one vertex. So we propose additional speedups. So the first speedup relies on the fact that we can extend this bound to the removal of various vertices at once. In particular, if we remove an independent set of vertices, that is, vertices which do not share any neighbors, then we can also upper bound the resulting minimum eigenvalue. So we can remove various vertices at once, and thus we will need to recompute this bound fewer times overall. The second speedup relies on using gradient methods to update the minimum eigenvalue and the corresponding eigenvector at each step of the algorithm. So the problem is that the minimum eigenvalue is in the flat part of the spectrum, so to speak. So on the right you can see a plot of the spectrum of the Congress dataset. And as you can see, the small eigenvalues are close to each other. And the problem with this is that eigenvalue algorithms have a rate of convergence which is usually dependent on how close these eigenvalues are together. So for instance, the convergence rate of power iteration depends exactly on this ratio. So we resort to gradient methods to estimate the minimum eigenvalue and corresponding eigenvector, which is much faster. The next speedup relies on low-rank updates of the eigendecomposition. So you might know that if you modify a matrix with a positive semi-definite perturbation of low rank, represented here as VV transposed, then the new eigenvalues of the modified matrix are the roots of the expression shown here. What's more, in our context, if we are careful about the vertices that we remove, then we pretty much can tell what the form of the involved matrices in the above polynomial is going to be. So we can carry out these computations very fast. And last, we propose a method to deal with big graphs. So computing the upper bound for the minimum eigenvalue in the case of very big graphs can be very costly. So what we do is instead we rely on a simple fact, which is that a graph is balanced if and only if all of its subgraphs are balanced. This is useful to us because this means that we can sample a large number of subgraphs randomly and make those balanced. And then we can look at the union of all the vertices that have been removed in this process from these subgraphs and remove those from the full graph. And we know that this will help us improve the balance of our original graph. And of course, we can run this in parallel for all sample subgraphs, and since they are much smaller, they are much faster to process. And doing this, we can really speed up the process for big graphs. And finally, we can actually, once we have found a balanced subgraph, we can restore some of the vertices that were removed early on, because they did violate balance in the beginning, but maybe now they are no longer involved in negative cycles, so we can add them to the graph again. And to do this, we actually design a very efficient restoration algorithm, which instead of naively testing whether or not each of the vertices will violate balance, we just rely on comparing two inner product between indicator vectors. And this is extremely fast and very convenient. So our final algorithm looks like this. While the graph is not balanced, we first remove a set of independent vertices based on the upper bound for the minimum eigenvalue that is given by the perturbation bound. We then update the minimum eigenpair for the resulting Laplacian based on either a gradient method or low-rank updates. And then we restore the vertices that are consistent with the balanced partition, relying on our fast restoration algorithm. The complexity of this method is dominated by computing the perturbation bound and updating the eigenpair, which is essentially squared in the size of the graph. And we can optionally carry out the sampling procedure to deal with big graphs. So we ran experiments on a number of datasets coming from real data. These are basically most of the datasets representing side networks that you can find online. There are not that many side network datasets so far, sadly. So we cover a variety of sizes from very small 16 vertices to reasonably large, over 100,000 vertices, and we also artificially augment some of these datasets to evaluate the scalability of our methods, reaching up to 1 million vertices and 35 million edges. We compare the performance of our approach to that of different heuristics coming from the literature. We run a greedy heuristic, also a heuristic based on some theoretical results in the side networks literature. And we also run a spectral method which was designed for a different problem but can still be used for finding balanced subgraphs. These are some of the results on real data. So for each dataset we report the maximum balanced subgraph found by each of the methods across a number of runs. And you can clearly see that our method finds the largest subgraphs in all cases, sometimes by a really significant margin. We also evaluated the methods on graphs with planted balance subgraphs in order to figure out the extent to which each of the algorithms is able to correctly find a balanced substructure that is known to be in the data. And we see that our method indeed succeeds in finding the planted subgraph in all cases, and in many instances it even finds a larger balanced subgraph. We do this by planting subgraphs on real data and also on some power law synthetic graphs. These are the running times on some of the larger datasets. Our method is not the fastest, but it is comparable to the fastest one of the competitive methods. The fastest method is the spectral method, but as we saw before, it fails in finding balanced subgraphs of a large size. Our method is sometimes about twice as slow as the next best method, but as we saw, it manages to find much larger balanced subgraphs and still in a reasonable time. This is an example of the graphs that we find. So this is a balanced subgraph found in the Bitcoin network, which represents trust and distrust between owners of the cryptocurrency. And we can see that there is a cluster of users that no one trusts. And this is indicative of a fraud network. This is another example based on the Congress network. So here, positive and negative edges represent unfavorable or favorable mentions between representatives in their speeches. And here, interestingly, there is a balance subgraph which is comprised of almost all the nodes in the network. That's 208 out of 219. And this is clearly representative of the party divide in the US Congress. So to conclude, we have proposed an efficient and principled algorithm for finding balance subgraphs based on spectral theory. In the process, we have derived a perturbation bound for the signed Laplacian. And we have shown our method to be effective in practice, but we offer no theoretical guarantees, so it would be interesting in the future to strive to produce some guarantees. And that's all. Thank you for listening. If you have any questions, do not hesitate to email me.